Hello students, how are you? I hope all of you are doing well. Today we will continue our discussion on torsion. In the last class we derived how to calculate the torsion shear stress. In today's class we will learn how to find the direction of the torsion and the second part of this at the end of these lectures I hope you will be able to solve the problem how to calculate the stress and strain due to torsion. So let's start. We are going to first our recap the what we have learned the other days. So, consider a shaft which is fixed at one end, and this shaft has a length L, and if we apply a torque excuse me, the one end, what will be happen? So if assume this is a straight line, and this straight line is change its position, this is the new line. So this angle is called phi, and this phi is my angle of twist, and this is rho. Rho is any point along the direction, along the radial direction, and this is the radius. C is the radius of the shaft, and this is my strain. From the in the last class we told that angle of twist phi equal to L, length of the shaft, gamma shear strain divided by rho. There is another equation we can define the angle of twist, that is phi is equal to torsion, and this is the torsion T. L, J is polar moment of inertia, and G is modulus of rigidity. And we also derived shear stress, maximum shear stress occur at the outer surface of this shaft, and this is This can be calculated by T multiplied by C divided by Z. We can rearrange this equation. T is equal to tau max divided by C multiplied by J. Okay, so all these equations are very important to solve any problem related to torsion. And for angular shaft, for circular solid circular shaft, for solid circular shaft, J is equal to half multiplied by pi C4. This is for the solid circular shaft. And for the hollow circular shaft, okay, this is CI, CI the circular inside radius, inner radius, and this is CO, outer radius. For the hollow circular shaft, let me write here. For hollow circular shaft, J is pi by 2 C CO outer form CI to the power 4. Okay, so these are the things we have learned in our last class. Now, so torque has, and the one thing I didn't mention in my other class is torque actually I did mention in the other class, torsion is a moment, right? So the torque, like as you remember, the moment has value and direction, right? So as I said, we when we calculate the moment, we said counterclockwise and clockwise. Similarly, the torsion has a direction, and these the proper determination of this direction is very important to solve any problem. So now we will see how can we decide the direction of the torsion. So the another thing I want to mention, the torsion, like moment, the torsion, the unit is Newton meter. Remember the moment, the unit is Newton meter. Similarly, the torsion has a unit, and this unit of torsion is Newton meter. Now let's consider this example. This is a shaft. This shaft is fixed at one end. Okay. Now if I rotate this shaft in counterclockwise, what is the sign of the torsion? So as you see, this can be determined by right hand rule. According to the right hand rule, both the torque and angle this torque and angle of twist phi is positive if thumb is directed outward from the shaft. Okay, the thumb is directed outward from the shaft, and let me hide this one for the time being. The, the as I said, the torque and angle of twist is positive if the thumb is directed outward when the fingers curl to give the tendency. Okay, for rotation. Let me say it again. The torque and angle of twist is positive if thumb is directed outward from the shaft when the fingers curl to give the tendency for rotation. As you see in this example, uh, this x direction is this way, the positive x direction is this way, and so my thumb is directed in this way, the right hand, the thumb of the right hand, while my other fingers actually curl to the direction of the rotation. Similarly, if I take another shaft and this shaft is rotating in this direction and my x is positive in left side, then this torque is positive and this angle of twist is also positive. Let me simplify this one. Now let's say this is a shaft and it is position A and it is position B, and my coordinate, this is my x coordinate, is positives along this direction, and this is my y coordinate. Okay, and this end, the right end, or the at A end, the torque is TA, and this end at the B end torque is TB. Okay, and this is my positive x. Okay. Now if I draw my right hand, Okay, this is my right hand. Now the torque and this is my angle of twist. The torque and angle of twist are positive if thumb is directed outward from the shaft when the fingers curl to give the tendency for rotation. So this is very important to understand the right hand rule because it actually gives you the direction. It helps you to decide the direction of the torque. Now according to this right hand rule, TA is positive and TB is negative. Please practice this with your right hand and see whether you can understand my explanation. Now let's solve a problem. So this is the problem. It's in the book example 5.2. In this problem, a shaft is held by two bearings, is supported by two bearings, and it is subject to three torques. One is at 42.5 kilopounds per inch, the other is 30 kilopounds inch, and the third one is 12.5 kilopounds inch. Determine the shear stress developed at points A, B located at section A. So in this figure C, as you see, this is the section A is zoomed here, and there are 2 points. One is here, this is A, and this is B. So we have to determine the shear stress developed at points A and B. Now remember this, the stresses will not be same in point A and point B because point A and point B are not located equally from the center. So here, if it is my center, the point A is located on the surface, outer surface of this plane of this section, and the point B is located somewhere in the middle. So So in order to solve this problem, we first need to calculate the torque. We first need to calculate the torque, the resultant torque I would like to say. And to do that, I'm there is a small interruption in my voice recording, and to do that, let's draw the free body diagram of the assembly. So this is example 5.2, okay, of the book. And so I want to draw, actually instead of 3D, I want to draw a 2D of the entire thing. So this is a shaft, and this shaft is supported at the two end by two bearings. Okay, so this is a bearing, and this is another bearing. Okay, and this one is 42.5 kilopounds in. This is in FPS unit. That's why actually in FPS units the force is pound and it is kilopound, and the distance is in inch. This is 30 kilopounds, and this is the last one is also is 12.5 kilopounds inch. Okay, now so this is the section is request. So this is the A section. Sorry, A section. And if I cut to this section, if I cut to this section, and as I know this, now there is a one thing, this since this is a bearing, there is no opposite torque. So that's why actually is this end there is no torque. In this end there is no torque. The torque here is 0. Okay, and this is 42.5, and this is 30 kilopascal inch. Sorry, this is 30 kilopascal inch. Now, in this section, there will be a torque. Let's say this torque is T, and this is my X, this is my Y. Now use right hand rule to find moment along X direction, to find summation of moment, summation of moment along X direction, and it should be 0. Now if I use the right hand rule, this 42.5 kilopascal inch is a positive, this minus 30 kilopascal inch is negative, and T is positive, it's going to be 0. If I solve this, the T is going to be 12.5 kilopascal inch. Okay. Now let me zoom in this section, this particular section. If I zoom here, if I zoom this section, and this is my element A, and if this is the element, this element will gonna experience shear force, and this is actually A, and this distance is, this element is located on the outer surface, so this is 0.75 inch, and this element, it's a B element. B element is experiencing shear force and shear stress. Now, as I know, um, so radius of the shaft is C, and it is 0.75 inch. Okay. Now the polar moment of inertia Z is equal to pi by 2 C4 to the power 4, pi by 2, 0.75 inch, and that is actually 0.4974 inch to the power 4. Now the stress at point A, stress at point A. So we know the stress at point A actually located at C, and so these all the points is rho. So at point A, my rho is equal to C equal to 0.75 inch. Okay. Now we know that tau A, stress equal to T rho J, and so tau A is going to be T C J divided by J. Now we know we got TC is 12.5 kilo pound inch. That means 12.5 kilo pound inch multiplied by 0.75 inch divided by 0.4974. So if I calculate correctly, the result is 18.9 KSI. Okay. Similarly, from the figure 5.11c, we know this point B is located 0.15 inch away from the center. Stress at point B is equal to, now stress at point B. So now at point B, my rho is equal to 0.15 inch. So tau B is going to T rho J. We know T is equal to 12.5 kilopounds inch, and J is 0.4974 inch to the power 4 multiplied by rho is equal to 0.15 inch equal to 3, that is going to be 3.77 KSI. So the stress at point A is 18.9 KSI, and the stress at point B is 3.77 kilopounds per inch square. Just to remind, KSI is kilopound per inch square. this is how to calculate the stress due to torsion, and in the next I'm going to solve another problem, and this problem you can find in the fundamental problem in the this is one of the fundamental problem of the book. Let me tell you the page number. And this is the next problem I am going to solve is also from the book, and this is book problem number F54, the page number 195 of 9th edition. Okay, I'm going to take a 1-minute break, and after the break we are going to solve this problem. Okay, so this is the problem. In this problem, a shaft is supported by two bearings. One is located at point A, the other one is located at point A, the another one is located at point D. So there are two belts, and the shaft is rotates by two belts. One is located at B, the another one is located at C. So we are the problem asks to determine the maximum shear stress developed in the 40 millimeter diameter shaft. So in order to solve this problem, we first figured out what is the resultant torque at at this rod, or this, at this shaft. Now, as you notice, this shaft is supported by two bearings, and in these bearings there is no reaction torque. It means if I cut the entire thing, let me draw this the entire thing. So if this is my, let me draw this way. This is my shaft. Okay. I'll try my best to draw it as perfectly as I can. So this is 6 kilonewton, this belt, and this belt is pulling 2 kilonewton, and this diameter, this radius of this is 150 millimeter. Okay, and this one and in this pulley is 10 kilonewton, this force, and this force is 4 kilonewton, and radius of this pulley is 100 millimeter. Okay, now the shaft is supported here at point A by bearing, and point B it is supported another bearing. Okay, okay. Now let's first cut to that section. So in this section, this is my B, this is my C. In this section, this is torque at AB. Now since, as I said, that bearing doesn't have any resistive torque, so TA is going to be 0. Okay. That means bearing, I'd like to write bearing reaction don't offer resistance to shaft rotation. That's why the torque at A is 0. So that's why TA is 0. Sorry, 0. Now, so TA AB is going to be 0. So here if this is my x and I take the summation of mx, so TAB, TA minus TAB equal to 0, so TAB is going to 0. Now this time let's cut the piece here. Okay, to cut the piece here, and if I cut it here and draw this, this is 6 kilonewton, this is 2 kilonewton. As I know, this distance, this radius is 150 millimeter. So there is a, and this torque is TBC. Okay, and this is my x, this is my y. So if I take summation of using right hand rule, the summation of f going to be 0, and then two so minus 6 kilo plus 6 kilonewton is multiplied by 0.15 meter. This is positive, and minus 2 kilonewton multiplied by 0.15 meter, and minus TBC is going to be 0. So if I rearrange this, TBC is 0.9 kilonewton meter minus 0.3 kilonewton meter is going to be 0.6 kilonewton meter, going to be 600 Newton meter. Okay, so we found the TBC. Similarly, if we cut the section and take this segment. Okay, this is the position D, D, and there is a torque, and we know TD is equal to 0. Okay, and this is TCD. So if you take the moment along the x direction, we can say TCD equal to 0. Let me second, TCD is going to TD equal to 0. So there is only torque, and that is TBC, and we learned TBC is equal to 600 Newton meter. Now, because we know the torque, the next step is find the maximum shear stress, and we can find the maximum shear stress Okay, we know the maximum shear stress equation. We know that tau max is going to TCC divided by J. We know this equation, and we know we can calculate Z by pi by 2 c to the power 4 pi by 2.024, and 0.02 is the C. As you said, the diameter is given is 400, diameter is given 200, 400 millimeter, so C is equal to 200 millimeter. If we convert it to meter, it's 40 meter, 40 millimeter, so it's a 20 millimeter, so this is 0.02 meter. Sorry for that. Now, we learn that T is, TBC is actually the T is 600 Newton meter multiplied by C is 0.02 meter, and J is pi by 2.024. So if we calculate this, tau max is going to be 47.7 10 to the 6 Pascal, to be 47.7 megapascal. This is the answer of this problem. This is a fundamental problem in the book, page number 195. So please solve the problem I already solved in today's lectures, and in the next class we will do couple of more problems, and please watch this lectures video and solve the example problem of the books. Talk to you guys later. So we have a office session tomorrow. Please watch these videos and attend the office session. If you have any questions, ask me there. Thanks for your time. Stay healthy and be safe.